Hello and welcome back to our channel. In this particular lesson, we are looking at pure math mechanics, tension in strings. We will focus on inelastic strings. We will look at inclined planes, connected particles, and pulleys. Please watch this video to the end and don't forget to subscribe and click on the notifications and share the video too. So what is tension? It is the force developed in a rope, string, or cable when stretched under an applied force. In this lesson, the strings considered are inelastic strings. Let us consider the example below. So consider a mass M attached to a fixed point with the aid of an inextensible string. And the tension in the system is T. The weight of the object is given by mg. Now, from the principle of statics, we have the equation T is equal to mg. That is, the tension of the string is equal to the weight of the object. Thus, for a body of mass 3 kg and taking G to be equal to 10 newtons per kilogram, the tension in the inelastic string T is equal to 30 newtons. Another example, a body of mass 5 kg is held in equilibrium under gravity by 2 inextensible light ropes. One rope is horizontal and the other is at an angle alpha to the horizontal as shown. The tension on the rope inclined at alpha to the horizontal is 72 newtons. Find the angle alpha, giving an answer to the nearest degree, and the tension in the horizontal rope, giving an answer to the nearest newton. So first of all, here we will have to resolve this 72 newton force. And for this object, the weight of this object is first of all given by 5 kilograms times gravity, that is 5g. This is how we mostly work in mechanics. Then resolving the 72 newtons force, vertically we are going to have 72 sine alpha, and horizontally, since this angle holds the line, we have 72 cos alpha. And since the system is in equilibrium, therefore means that horizontally we have sine alpha, or vertically, let's start vertically. We will have 72 sine alpha to be equal to the weight, that's the tension. The y component of the tension is equal to the weight. And from there, sine alpha will be equal to 5g on 72. And we are taking g to be 10 in this particular equation. So sine alpha will be equal to 0.6805, giving us an alpha value of 43 degrees to the nearest whole number as they set to the nearest degree. Now the tension in the string, for the tension in the string, we work with the horizontal components, and T will be equal to 52.8 newton, because we know that T minus 72 cos alpha is equal to 0, since the system is in equilibrium, and that gives us T to be equal to 52.8 newtons. The nearest newton you have 53 newtons. Question 3, a particle P is attached to one end of a light inextensible string and the other end is fixed at the point A. O. A horizontal force of magnitude 12 newtons is applied to P. This is P. The particle P is in equilibrium with the string taut and OP making an angle of 20 degrees downward vertical as shown. Find the tension in the string and the weight of the rope P. Weight of the mass P. So as usual, we start by resolving these forces into its components. First of all, the weight of P is given by W, where W is mg. Then we have the vertical component of this string, of this tension. This will give us T, because the tension of the string is T. So we have T sine alpha T sine alpha horizontally, and vertically you have T cos alpha. So we note that this angle here of 20 degrees is the same angle here, 20 degrees. So that's why we're having T cos 20 degrees here. Then horizontally, we have T sine 20 degrees. And now that the system is in equilibrium, it means sum of upward forces should be equal to sum of downward forces, and sum of forces to the left equals sum of forces to the right. So looking at the horizontal components, we will have T sine 20 to be equal to 12 newtons. So we can find the tension directly, which is equal to 12 divided by sine 20, giving us a value of 35.1 newtons. Now for the vertical component, upward force equals downward force, at W will be equal to T cos 20 degrees. So, but we already have the value of T to be 35.1. So W will be equal to 35.1 times cos 20. That gives us 33.0 newtons. Example 4, a particle P is held in equilibrium under gravity by two lightning extensible strings. One string is inclined at an angle of 60 degrees to the horizontal and has a tension of 40 newtons. The other string is inclined at an angle of 40 degrees to the horizontal and has a tension T newtons as shown. Find to three significant figures the value of T and the weight P. As usual, we always start by resolving the forces involved. So our weight here will be mg. The tension T newtons is resolved into its horizontal and vertical components. Horizontally, we are going to have T cos 40 degrees, and vertically we will have T sine 40 degrees. Now for the 40 newtons force, the horizontal component will give us 40 cos 60, and for the vertical component we will have 40 sine 60. Now from the principles of statics, upward forces equals downward forces, sum of forces to the left equals sum of forces to the right. So this will give us T cos 40 minus 40 cos 60 to be equal to 0 for the horizontal components. From here, we can find the value of T, which will be equal to 40 cos 60 divided by cos 40. And that gives us 26.1 Newton to three significant figures as required by the equation. Then for the vertical components, we have the weight of this string to be equal to T sine 40 plus 40 sine 60. But we have our T to be 26.1 newtons, and substituting this value and simplifying will give us 51.4 newtons. The next example, a body of mass 5 kg lies on a smooth horizontal table and is connected over a smooth pulley to another mass 5 kg, hanging over an inextensible string. Find the acceleration of the system, taking G to be equal to 10 newtons per kilograms. So we start by sketching the free body diagram. This is the mass of 3 kg that lies on the smooth horizontal table. The smooth horizontal table is this. And we have a pulley connected to it. So a string is connected from this 3 m, or this 3 kilograms mass, to another particle of 5 kilograms. So we now, the next thing is to indicate the forces that are acting. Starting with the hanging mass, we are going to have its weight to be given by 5 kg by 5 kg. So this gives us 5 kg times G, and then the tension in the string is T. Since this string is the same and it just passes over the smooth pulley, since the pulley is smooth, it means frictional forces are negligible. So we now look at the mass on the smooth table. The tension is also T. And since the pulley is smooth, the friction is negligible. Now, as we know, the 5 kg has a higher weight. So this one has a higher weight. And therefore, it should normally pull this 3 kg along this plane in this direction. So this is making the decision on the acceleration state. The system will accelerate in this direction. And we note that the tension in the string and the accelerations of the system are the same. So now, starting with this first one that is hanging vertically, we have the equation 5g minus t to be equal to its mass times its acceleration. Since it's going to move downwards, so the resultant force will be downwards. So we have 5g minus tension should be equal to the mass of this particle times the acceleration of the system. Question 1. And for the other one that is on the horizontal table, there is no resistant forces. The plane is smooth, so the friction is negligible. The only force acting on it should be this tension. And since the particle is moving, this tension should be equal to the mass of the particle times the acceleration. From here, if we add the two equations, we are going to have 5g to be equal to 8a, and that will give us acceleration of the system to be equal to 5 on 8g, where g is 10. Hence, we can find the tension by substituting this acceleration in, let's use equation 2, and the tension will be equal to 15 on 8 g. G here is equal to 10. So in the exam, you simplify by putting the value of 10 here, and then you continue. Otherwise, if not given, you leave your answer in terms of g. Another example, a particle of mass 2m lies on a rough horizontal table. In this case now, the table is rough. P is connected by a light inextensible string passing over a smooth pulley fixed at the edge of a table to another particle Q of mass 5m hanging freely. The system is released from rest with the string taut and hanging part vertical. If the acceleration of the system is of magnitude 0.5 meters per squared second, find the coefficient of friction between the first particle and the table and the tension in the string. So we start by a free body diagram. This is a table. A particle of mass 2m rests on this table, and the weight of this particle will be 2m times gravity. And it is having a normal reaction also of 2mg from Newton's laws, third law. Then it is connected over a pulley to another particle. So there is tension in this string connected to another particle which is hanging now vertically and has a mass of 5m. So the weight of this one will be equal to 5mg. Then equally, since there is friction on the horizontal table, the table is not smooth. There is frictional force acting. So this is indicated by 2 mu mg, because the frictional force will be equal to the coefficient of friction times the normal reaction. Normal reaction here is 2 mg. So times mu gives us 2 mu mg. The acceleration of this system will be downwards because, as we know, this 5 kilograms, this 5m mass should normally pull this 2m mass because you see that the system accelerates. And the acceleration of the system has been given as 3 as 0.5 and given as 0.5. So the acceleration of the system is 0.5. So let's start with the 2m mass. Resolve the force for the 2m mass. So for the 2m mass, we have T minus 2 mu mg to be equal to the mass times the acceleration. The mass is 2m times acceleration of 0.5. That will just give us m. So T minus 2 mu mg should be equal to the mass of this 2m. That is 2m times acceleration, which is 0.5. That gives us just m. Then for the 5m mass, we have downward components. That is 5 mg minus tension in the string should be equal to this mass of 5 mg. This mass of 5m times the acceleration of the system. So we'll have 5m times 0.5, which is 2.5 m. So from here, if we add the two equations, we are going to have 5m minus 2 mu mg to be 3.5 m. And we will have mu to be equal to 0.175, taking g as 10. Now, for the B part of the equation, we have find the tension in the string. For the tension in the string, we are going to look at equation 1, first equation, and we substitute this value of mu in the equation, and we will have the tension in the string to be equal to 4.5 m. Tension in the string will be equal to 4.5 m. Example 7, one end of an inextensible string of length 3 meters is fastened to a fixed point O, 2 meters above the horizontal ground. A small particle is attached to the end of the string. The particle describes a horizontal circle 1 meter below O. Find in terms of G the tension in the string and the angular velocity of the particle. So we have one end of an inextensible string of length 3 meters is fastened to a point O. And we are being told that it is 2 meters above the ground. So it is fastened at this point. A small particle is attached to one end of the string. Small particle attached to one end of the string. The particle describes a horizontal circle 1 meter above the ground. So this distance from this particle to the ground here is 1 meter. You can form a small triangle there, as you can see. And we are now to find, in terms of G, the tension in the string and the angular velocity of the particle. So if you resolve this force, this tension in the string, and using the weight of this mass to be mg, then you have this angle theta to be given by, because this distance from here to here is the hypotenuse 3, and the height where this particle finds itself is 1. Therefore, this remaining distance according to Pythagoras will give us √8. So we form this right angle triangle, and this angle is theta. So from here we have a t cos theta, resolving this tension, t cos theta, because if this angle is theta here, then at this point this angle is also theta. So t cos theta should be equal to mg, and they resolve to have the horizontal components. We have t sine theta. T sine theta should be equal to the angular force acting, the centripetal force acting towards the center of this circle. So from Pythagoras, we have this triangle to give us cos theta, which is equal to 1/3 cos theta, adjacent of hypotenuse, and sine theta is 8/3. So for the vertical component, we have t cos theta equals mg. So t times 1/3, which is t/3 equals mg, and t will be equal to 3 mg. For the other components, for the horizontal component, t sine theta should be equal to mrw squared, where rw squared is the centripetal acceleration. Whenever you're talking about horizontal and vertical centers, circles, talk about the centripetal acceleration, which is the acceleration for particles moving in circular paths. So the centripetal acceleration is given by mrw squared, or mv squared on r. So from here, we will have g to be equal to w squared, simplifying all through, where this w here is the angular velocity. So w will be equal to √g radians per second. So the angular velocity of the particle is √g radians per second. Another example, two particles A and B are connected by light inextensible string which passes over a smooth fixed pulley. The mass of A is 4 kg and the mass of B is M, where M is greater than the 4 kg. The mass is released from rest with the string taut and the hanging parts of the string are vertical as shown. After release, the tension in the string is 1/4 mg. Find A, the magnitude of the acceleration of the particles, and B, the value of M. State how you use the fact that the string is inextensible. So we start by resolving the forces on this pulley. You have the mass of 4 kg. There's tension in it, and it has a weight of 4 times g. So 4g, and the tension is T. But they've given us the tension to be equal to 1/4 g. Then for the other mass B, which is greater than this 4 kg, it equally has a weight of mg and the tension is T. Now we are being told the system is released from rest. And since this mass is the greater mass, this pulley here is smooth, we know that this greater mass should normally pull the system downwards, this direction. So that we decide now the acceleration of the system is going to be downwards with respect to the M mass, while this other mass of 4 kg will move upwards. Okay, so for the particle B, start B, for B, we have mg, the direction downwards, so mg minus tension should be equal to the mass times the acceleration. So mg minus 1/4 mg, because the tension is 1/4 mg, should equal to ma. So all the m's to cancel out, we'll be left with g minus 1/4 g, which is 3/4 g, should be equal to ma, and a will be equal to 3/4 g. A is equal to 3/4 g. Now let's find the value of m. To find the value of m, let's consider the particle A. So for A, the tension, because it's going to move upwards, minus 4g should be equal to its mass times its acceleration. The acceleration of the system is already equal to 3/4 g. So we have 1/4 mg, which is the tension, minus 4g should be equal to 4 into 3/4 g. This will give us 1/4 m to be equal to 7, and m will be equal to 28 kg. M is equal to the mass is 28 kg. That's how you have used the fact that the string is inextensible. So here, the acceleration, as we know, of this particle upwards is equal to the acceleration of this system, this other one downwards. Their magnitudes are the same, the only difference is direction. This one moves upwards while this other one moves downwards, but the magnitudes of the accelerations are the same. So that's how we have used the fact that the strings are inextensible by working with that acceleration. Example 9, the figure shows a block P of mass 0.6 kg resting on the smooth surface of a horizontal table. Inextensible like strings connect P to blocks A and B, which hang freely over light smooth pulleys placed at opposite parallel edges of the table. The masses of A and B are 0.3 kg and 0.5 kg respectively. All portions of the string are taut and perpendicular to their respective edges of the table. The system is released from rest. Calculate A, the common magnitude of the acceleration of the blocks, and B, the tension in the strings. So unlike all the other cases, this case is special because though we have the same string, the tension in this string A is different from the tension here. This is the trick in this question. And why does this happen? This is because we have a weight here on this table, resting on this smooth table. So the tension in this rope A will also depend on the weight of this mass A, while the tension in B depends also on the mass B. So this case is actually different. So the tension on this side, we have two different strings, as you can see. This is the different string from this other string, which is different. The particles are connected, but the tensions are not the same. So we are going to label these tensions T1 and T2. Let's start by resolving our forces. So for A, the weight is 0.3 G, and the tension in it is, call it T1. Then for B, the weight is 0.5 G, and the tension in this string is T2. Or if the particle does rest on the smooth table, the tension in this direction, the pulling force in this direction is T1. On the right, we have T2, the same tension. Now, these particles are released from rest. The system is released from rest, as the question says. So if this is released from rest, we believe, or we note, or we know that this 0.5 should normally pull this other 0.3. So the acceleration of this system should be towards the right, this way downwards. So the acceleration is in this direction. And for the mass A, we will have T1 minus 0.3 G should be equal to the mass 0.3 times the acceleration of the system, which is A, equation 1. Then for the particle P, we have, since it's going to move in direction, we have T2 minus T1 should be equal to MA. So T2 minus T1 should be equal to its mass times its acceleration, 0.6A. And for the mass B, we have 0.5 G minus its tension T2 should be equal to its mass 0.5 times acceleration A. So the tensions are different, but the acceleration of the system is the same, unlike the other questions, as I've said. Now, this gives us a sum of three equations, three unknowns, but we can directly solve for the acceleration. If you just add equations 1, 2, and 3, we'll see how the parameters will disappear. So 1, 2 plus 3 will give us, we have minus 0.3 G plus 0.5 G. So we have 0.2 G equals, adding all of this, we have 1.4 A. And our A is equal to 0.2 times 9.8 on 1.4. So in this question, we took G as 9.8. So acceleration is 1.4 meters per second, or per squared second. Now the tension in the strings, this question is already finished, because after doing all of this, then you cannot make a mistake in finding all these other parameters. So we substitute this one in T1, in equation 1, we'll have a T1 to be equal to 3.36 newtons. And substituting this in equation 3, we equally have a T2, in equation 2, a T2 will be equal to 0.6 times A plus T1. That gives us 4.2 newtons. This question looks very tough. Once you understand that the tensions in the strings are different, but the acceleration of the system is the same, then you have solved this question in a blink. All right, the second to the last example, two particles A and B of mass 8 kg and 10 kg respectively are connected by light inextensible strings which pass over a light smooth pulley P. Particle B rests on smooth horizontal table and A rests on a smooth plane inclined 30 degrees to the horizontal, the string taut, and perpendicular lines of intersection of the table and the plane as shown. The system is released from rest. Find the magnitude of the acceleration B. So let's start with this. And the tension in the string, the distance covered by B in the first 2 seconds of motion, given that B does not reach the pulley. Given that B does not reach the pulley. Okay. So we start by resolving these components of HG parallel to the plane. We have 8G sine theta, that is sine 30. And for B, the tension in the string is T. In fact, the same string, so the tensions are the same. Then we know that from the equation as they have said, the particle accelerates, or the system accelerates in this direction. So at this point for B, we will have T to be equal to its mass times acceleration. There is no other force acting on B apart from this tension. So this tension should be equal to the mass of B times its acceleration. And then for A, we have, since it moves downwards, so we have AG sine 30 minus the tension should be equal to the mass times the acceleration of the system. So adding the two, equation 1 and 2, we will have AG sine 30 to be equal to 18A, and from there A will be equal to AG sine 30 on 18A, which is equal to 2 on 9G. We have 2 on 9G as the acceleration of the system. The tension in the string, substituting this value in equation 1, we will have T to be equal to 20G on 9, which is equal to 21.7 newtons. Next, we have U equals 0. That's for C, the distance covered by B in the first 2 seconds of motion. So you know it starts from rest, so U equals 0. The acceleration of the system is 2 on 9G. Time is 2 seconds. So the distance covered by B will be given by S equals UT plus half AT squared, where substituting the parameters, we have half into 2 on 9G times 2 squared. And this will be equal to 4G on 9 meters. So the total distance covered is 4G on 9 meters. Please, guys, don't forget to subscribe to this YouTube channel. That is the only way you can really patronize us, and to leave your comments. And don't forget to click on the notifications bell so that when we release another beautiful video to serve you out there, you are immediately notified. Thank you so much, and don't forget to share this video. So finally, here we have 4.35 meters when we substitute the value of G. All right, question 11. A fixed wedge has 2 plane faces, each inclined at 30 degrees to the horizontal. 2 particles, A and B, of respective masses 3m and m, are attached to the ends of light inextensible string. Attached to this end. Each particle moves on one of the plane faces of the wedge. The string passes over a smooth light fixed pulley at the top of the wedge. The face on which A moves is smooth. So this other face, this other side of the pulley is smooth, while the face on which B moves is rough. So one of the faces is rough this time. The coefficient of friction between B and this face is mu. So this is the coefficient of friction here is mu. Particle A is held at rest. Held at rest in the string tooth. The string lies in the same vertical plane as lines of greatest slope on each plane face of the wedge as shown. The particles are released from rest to start moving. Particle A moves downwards. So the direction of motion is this direction downwards. And B moves upwards. The acceleration of A and B each have magnitude of 1 on 10G. A, by considering the motion of A, instructions must be followed. Find in terms of M and G the tension in the string. So let's start with this part. By considering the motion of A, we resolve this force. We are going to have 3mg sine 30. And then we have the tension in the string. This is what we have. And the acceleration of this system, we have been told, is 1 on 10G. So this will give us, for A, we have 3mg sine 30 minus T to be equal to its mass times the acceleration. So you simplify this, we'll have T to be equal to 3 on 2 mg minus 3 on 10 mg, which is equal to 6 on 5 mg. So that gives us 6 on 5 mg. Okay. Then we continue with the equation B. By considering the motion of B, find the value of mu. So we now resolve B as well. It has a normal component, R, and the weight of B is mg. The the components parallel to the plane will be mg sine 30, and frictional force also acts. Then equally, we have this normal reaction, which is equal to this perpendicular component to the plane, which is mg cos 30. So these are the forces that you have on G. First, it has a frictional force acting. Since the particle is going to move upwards, friction should act in this direction downwards. Then the component of its weight perpendicular to this plane is mg sine 30, which acts in this direction. So parallel to this plane, downwards, we have two components, and upwards, we have one component. But since the particle finally moves upwards, means the upper component, the tension is greater than the two of these. However, to start looking for mu, we first of all have to find the value of R. And we have seen that R is equal to mg cos 30. Now let us consider the components parallel to the plane. The components parallel to the plane, we consider the frictional force, which is mu R. But we know that the R is equal to mg cos 30. So F will be equal to mu times mg cos 30, which is mu mg cos 30. The equation now for the parallel components will give us T minus F minus mg sine 30 equals the mass m times acceleration. Substituting the values here, we'll have for T is 6.5 mg minus F is mu mg cos 30 minus mg sine 30. That gives us m times A. Okay. So we have 6.5 mg minus mu mg into 0.866 minus mg into 0.5 equals 0.1 mg. That will give us a mu value to be equal to 0.693. So mu equals 0.693. Can equally do it, leave the answer as a fraction. And next, for C, to find the resultant force exerted by the string on the pulley. So the pulley is at this point P, and the forces on this point P, we have this T on the left and T on the right. And since these angles are both 30 degrees, it means that the force exerted by tension on the left is equal to the force exerted by tension on the right. So these components will be resolving this tension. These components horizontally will cancel out. So the horizontal components in the horizontal direction will cancel out, because here we have T sine 60 to the right and T sine 60 to the left. So there is balance. There is no move the horizontal direction. Vertically, we now have T cos 60 plus T cos 60. So at P, we have there is a resultant will be equal to 2T cos 60 for each of the components. And that will give us 2 into 6 on 5 mg into a half. So the reaction is 6.5 mg. So this is what we have seen in this question. One of the planes is smooth, and equally have been asked for the reaction of these two pulleys on the plane. This paper 3 is a very, very good type. You mostly find this in past questions. The last question of the day. Don't forget to subscribe, guys, and please click on the notifications and leave your comments on our videos. We equally implore you to share this video so that it may reach others. That's the way that you're going to patronize us in this work that we're doing. We thank you so much for always being there. And please, if you have your comments, always leave them so that we know how we can serve you better. So this question, a fixed wedge, it's already drawn diagrammatically. So a fixed wedge whose smooth faces, so the faces in this case are now smooth, inclined at 30 and 70 the horizontal, has a small, smooth fixed pulley on the top at point B. Pulley here is smooth and fixed. Lightning extensible strings pass over it, connect particles P and Q. They have masses of 2 and 3 respectively attached at the ends. The figure shows a vertical cross-section of the wedge, AB. AC, and you have been told that AB and AC are lines of greatest slope. So AB and AC are lines of greatest slope of the faces along P and Q respectively, of which they can slide. The particles are released from rest at time t equals 0 with a string tooth. Assuming that P has not reached B, Means since they're going to move, P is going to move upwards towards B, while Q will move downwards. So assuming that P has not reached B and Q has not reached C, so Q has not also reached C, find the distance through which each particle has moved when T equals 0.75 seconds. Of course, the particles cover the same distance because string is taut, okay? And this one has not reached this point, while this has not reached this point. All right, so let us start by this. We resolve these forces. For P, we have 2G newtons. Then tension acts in this direction. The normal reaction is R, okay? And then for B, for the particle Q, the normal reaction is R, let's call it R prime, the weight is 3G. Acceleration is going to be downwards, as we can see. Now let us see how we resolve this. So for the particle P, we have T minus 2G sine 30. This component downwards. So minus 2G sine 30 because it's mass times its acceleration. And for Q, since it's moving downwards, we have 3G sine 70, that's the downwards component, minus the tension in the string should be equal to its mass times its acceleration. So adding these two equations, we are going to have acceleration to be equal to 3.565. The B part, the distance through which each particle has moved when T equals 0.75 seconds. So initially they're at rest, so U is 0. Acceleration is this, that's the time. So the distance we given by S equals UT plus half AT squared. We already have our A to be equals 3.565. We substitute this value and that gives us 1.0 meter. Now, this last part is very important. That's the addition to this equation. That's one knowledge we have to gain. When T equals 0.75 seconds, the string breaks. This is the case now of broken strings, okay? String breaks and the subsequent motion P comes to instantaneous rest at time T1. Assume that P has not reached B, calculate the time. So we are calculating time. So in G, we are calculating the time. So we know from equation 1 that T is equal to 2G sine 30. So our tension, that's the B part. Okay, we skipped out this part. The tension in the string, tension is 16.93 newtons. Okay, the magnitude and direction of the resultant force exerted on the pulley. The magnitude and direction of the resultant force exerted on the pulley. So this resultant direction will be given by the direction. As you can see, the direction is passing through the line that bisects the diagonal of this parallelogram. That's the direction of the force. And now we have T cos 40, T cos 40. So that will give us 2T cos 40 because these components for this tension, you have T cos 40, this other component have T cos 40. That will be the result. In these other directions, they will cancel out. Right, so that gives us the normal reaction on the pulley to be 25.939 newtons. Now let's move to this part where the string breaks. The final speed of the part of the motion is when the string is taut. So when the string is taut, this will be the initial speed of P after the string breaks. So our U is equal to 0, acceleration is 3.565 T 0.75. So we are calculating V. So that will be the value of V. So as you can see, this is what actually happens. So for P, after the string breaks, this is what we're going to have. So we have minus 2G sine 30 equals 2A. Minus 2G sine 30 equals its mass times its acceleration because we're moving in this direction, right? And the tension is equal to 0 because the string has broken. So that's why the t is no more here. T minus 2g sine 30. We just have a t minus 2g sine 30 equals 2a because the string has broken. So the acceleration of the particle will be minus g sine 30, which is equal to minus 0.5g. So we'll be in this opposite direction now. Okay. So from there we have u to be equal to 2.674 from this calculation. That's the initial velocity now, because the final velocity at the point where it breaks when it was moving now becomes the initial velocity when you change direction. Its final velocity is going to be 0 when it comes to rest. Acceleration is negative 0.5 g as you have seen, at t equals t1. So using v equals u plus at, we will have t1 to be equal to 0.5457. So I implore you to look at this question again. It's one of the most complicated questions throughout these tutorials. We wish you the best as you prepare for your exams, and please don't forget to subscribe. Thank you so much. You can equally revise concepts of vertical and horizontal circles if you've been in one of our videos, but here are some few summaries. So for a circle of this form, this is now a vertical circle. One of our questions in this problem was on horizontal circles. Now we have to know that vertical circles at the top, we have mg plus t equals the centripetal force, mv squared on r. The top, this top position up here. And then at the middle, these middle positions, we just have the t, the tension on the string to be equal to mv squared on r, that's the centripetal force at these both positions. While at the bottom, the tension is equal to mv squared on r plus mg. So at the top, tension is mv squared on r minus mg, while at the bottom, t is mv squared on r plus mg. So for the string at an angle theta to the vertical, any other position, we have mg cos theta plus t to be equal to the centripetal force. So at any other point apart from these points, we have mg cos theta plus t equals mv squared on r. Thank you guys so much for being there. In our next videos, please don't forget to subscribe and click on the notifications so that once you upload a video, you are notified at once. Thank you for sharing our video. Watch also the inclined planes, projectiles, momentum, work energy, and power, and a lot more. Thank you so much. Stay tuned and bye-bye.